We're gonna start chapter 15 now, which is impulse and momentum. And this again, this is principle of linear impulse and momentum. And so throughout this section, we're going to use this equation here. It's going to be like M1 V1. And on the right-hand side, we're going to have like M2 V2. And again, that's sort of this is conservation momentum. But then we're going to have like impulse in between. This is going to be the summation of the integral of f dt. And so remember before we had work here. So remember work was force times distance. So now for impulse, this is going to be force times time. So again, this term right here is usually called the linear impulse. And if f is constant, this term becomes f delta x or f delta s. Excuse me, f delta t. Yeah, it'll become f delta t if force is constant. Like I said before, we had work, which was when force was constant, it was work times delta s. Now we'll have force times delta t. And so we're going to do some problems related to that. And again, sometimes this will be like a sum of momentum. But here in this particular case, we maybe just have one mass, but we'll look at multiple masses as well. And let me do an example which I didn't hand out in the handouts there. I think this is one of the fundamental problems. I can write the problem down. This was F15.3. We're going to now look at this problem, F15-3. F15-3 says the motor exerts a force of 20 t squared newtons on the cable where t is in seconds. Determine the speed of the 25 kilogram crate when t is 4 seconds. The coefficients of static and kinetic friction between the crate and the plane are 0.3 and 0.25 respectively. So you have like I said, this is not one of the ones I handed you. So if I can make it right here. So we have like a motor here pulling a crate, and the force is going to be 20 t squared newtons. So it's motor's pulling the crate in this direction. And then how fast, the question is how fast will the crate be moving after 4 seconds? and it's 25 kilograms. Then we're also given that the static friction, mu s, is 0.3, and the kinetic friction we're given is 0.25. Remember, the static friction is how much it takes to get it started, and the kinetic friction is how much friction there is, or well, like the static in when it's not moving. So again, this is like for not moving, and then this is the coefficient when it is moving. So anytime we have a problem like this, if the package is still to start with, we have to find out when it starts moving. And of course, to do that, we have to figure out how much force is it going to take. To start it moving. And so we'll take a look at that. So again, if we have like 25 kilograms, then of course this force here is going to be, so the normal force will be 25 kilograms times 9.81, which is 245.25 newtons. And then the friction. So first of all, we need the static friction. Is going to be mu times this, which is 0.3 times 245.25, which are around 73.6 newtons. So that's the static friction force. So therefore, so we need to overcome friction. So now the force that the motor's pulling is 20t squared. So therefore, the force has to equal the friction force for it to start moving. And the force from the motor is 20t squared. And the friction force we got up here was 73.6. So if we solve that for t, it gives us around 1.92 seconds. The crate will begin to move. And so now we're going to use our equation M1 plus the impulse. We're going to use M1 V1 plus the impulse equal M2 V2. So that's what we want to use. And we're going to have to find out what this term right here is. So let's find that. There's going to be integral of f dt. And we want to know what's going to happen after 4 seconds, but we know the crate doesn't begin to move until 1.92 seconds. So we integrate this thing. We're going to integrate it from 1.92 up to 4 seconds. Again, because it's not moving until it gets 1.92 seconds. And the force acting on this is going to be the motor, which is going to pull it at 20t squared. But then the friction force is going to be operating in the opposite direction. So it's going to be minus 73.6. Again, so that's going to be the friction force that's going to, you know what? I made a mistake here. Scratch that. We're going to have kinetic friction now. So that's going to be 0.25 times our 245.25 dt. Let me rewrite that. That's pretty messy. So it's going to be 1.92 to 4 20t squared minus 0.25 245.25 dt. Again, this is going to be mu of k. This is the normal force. Sometimes we call it NC. So in other words, this is friction here. So this is friction, and this is the force from the motor. And when you integrate this, I won't go through the steps, but when we integrate this, this is going to give you around 252, 252, more or less. And then that's our impulse. Again, let's go back to our equation. M1 V1 plus the integral F dt, M2 V2. Again, it's starting out from rest, so this is going to be 0. And over here, this is going to be 252. And our mass is 25 kilograms. Our V2 is here. As you can see, this comes out to around 10. If you put in your calculator, around 10.1 approximately meters per second. Next, we're going to look at this problem from your book 15-7. Crates A and B weigh 150 pounds respectively. If they start from rest, determine their speed when t is 5 seconds. Also find the force exerted by crate A on crate B during the motion. The coefficient of kinetic friction between the crates and the ground is 0.25. And you remember one thing nice about when you're in pounds, the normal force and then is also going to be in pounds. So it's going to be like 100-pound force here, 50-pound force here. And then the friction, we're told in this case that the kinetic friction, let's see, if they start from rest, so mu k is given as 0.25. So our friction force in this first box here is going to be 0.25 times 100. So the friction force here is going to be 25 pounds. And over here, the friction force is going to be 0.25 times 50, which is going to be 12.5 pounds. So that's the friction force. And I guess, you know, they don't tell us the static friction, so I guess they're assuming it's going to start right away. You can see the force applied is going to be greater at least than the force due to the kinetic coefficient. So I guess we have to assume it's going to just start from rest since they don't give us the static one. So again, keep in mind that we're going to use M1 V1 plus our integral f dt equals M2 V2. But in this case here, everything is a constant force. How we have a constant 50-pound pushing, 25-pound resisting, 25 resisting. Again, those are our friction forces that are in the opposite direction. So our mass to start with, again, this is going to be started at rest, so it's going to be 0. So over here, we can just write this force right here is 50 minus our friction force. And it says they want to know what happens after 5 seconds. So this is going to be 5 seconds here. Equals M2. And that's going to be like our total mass. Times V2, like this. So all we did here, again, because the forces are constant, we didn't need to integrate anything. We just added up the forces acting in the positive direction, which is the force applied, minus the friction forces, times the total number of seconds, which is 5 seconds. So in other words, we just used F delta T is what we used in this case because force was constant. The right-hand side is the mass. Of course, when we're in English units, it's going to be the weight divided by 32.2. And if you put that in your calculator, you get V2 is 13.42 meters per second. And the second thing we need to find out is how much force is exerted by crate A on crate B. So we'll take a look at crate B, which is 50 pounds. Once again, we know crate B has a friction force underneath it of 12.5 pounds. And we want to know what this force acting on it here is. We don't know what F is. But we do know the final velocity, right? We know that both blocks are going to move at this velocity here. So once again, for this part, use M1 V1 plus, again, it's going to be the integral, but once again, since we're constant, we can use delta T, F delta T equals M2 V2. Again, we're starting at 0. And now the forces, we're going to have this unknown force F pushing it forward. And then minus the 12.5. And it's all applied for 5 seconds. And just as before, the right-hand side is 50 pounds this time. Remember, we're just focusing on block B. We want to see what's happening to block B. So it's 50 pounds divided by 32.2. We know that they're moving at 13.42 seconds. And if you solve, so in other words, if you solve for F, so it's going to be F times 5 minus 12.5 times 5. That's 12.5 times 5 is 50 over 32.2, 13.42. You put that on your calculator, you get the force applied to block B is about 16.7 pounds. Next, we're going to look at this problem, 15-13. The 2.5 megagram van is traveling with a speed of 100 kilometers per hour when the brakes are applied and all four wheels lock. If the speed decreases to 40 kilometers per hour in 5 seconds, determine the coefficient of kinetic friction between the tires and the road. So we have this van traveling at a certain speed. Again, I usually like when it gives the megagrams, so I don't make a mistake, I usually just change it to kilograms, so it's going to be 2,500 kilograms. And it's moving at 100 kilometers per hour. So that'd be like 100,000 meters per hour. And if we divide that by 3,600, that'll give us meters per second. So it'll be 27.8 meters per second. And once again, look at the reaction here. This is going to be 2,500 times 9.81, 24,525 newtons. And we're going to apply the brakes, and the speed is going to decrease. So the final speed is going to be 40 kilometers per hour. Again, so that's 40,000 meters an hour. If you divide this by 3,600, we get 11.11 meters per second. So that's going to be our final velocity. And they want to know the kinetic friction, coefficient of kinetic friction. What is mu k? So again, all we have to do is use m1 v1 plus the integral f dt equal m2 v2. And so once again, the force is going to be constant, so we can rewrite this as just f dt. So over here, we're just going to use f delta t. And so for our M1, we're starting, again, we have 2,500 kilogram car. It's traveling at 27.8 meters per second. Now, the only force that's going to be applied when we apply the brakes is going to be friction force. In other words, when the brakes are applied, there's going to be a friction force that's going to try to slow it down. And so that's going to be F delta T equals 2,500 times 11.11. And if we multiply this out, we get like 69,500. Now, again, our friction force right here is going to be mu of k times our normal force. Again, that's usually what the friction force is. And our delta t, we know that's going to be 5 seconds, we're told. And this is 27.78. So just go one step further. We know that the normal force is 24,525 times 5 seconds, 27,778. All we have to do is put that in our calculator, and we get the kinetic friction is around 0.34. Next, we're going to do this problem, 15-21. It has a tugboat pulling this barge. And it says if it takes 35 seconds for the 500 megagram tugboat to increase its speed uniformly to 25 kilometers per hour, starting from rest, determine the force on the rope on the tugboat. The propeller provides a propulsion force F, which gives the tugboat forward motion, whereas the barge moves freely. Also determine the force F acting on the tugboat. The barge has a mass of 75 megagrams. So it's starting out, say V1 is 0, and then V2 is going to be our 2,500, 25 kilometers per hour. So 25,000 divided by 3,600 gives us 6.94 meters per second. If you change it, and then the change in time we're given is 35 seconds. And apparently there's no friction or anything. So what we have in the first part is both the barge and the tugboat are working together, and they're increasing the speed. So there's some force that's kind of pulling it, obviously the force from those pulling the total mass and gets it up to this speed. So we can say, once again, starting from 0, m1 v1, plus, again, the integral of f dt. Once again, since here we can see the force is going to be constant, so we can just use f dt. Let's just jump right to that. m2 v2 here. Once again, we're starting at 0, so it's be plus 35 seconds for a time. And again, the mass is going to be the total mass, 75,000 plus 50,000. And our final velocity is 6.94. And so it's going to be around 24,786 newtons is what it's going to take to get this thing starting at 0 and getting it up to 6.94 meters per second. So then any questions on that first part? On the first part. So the second part, then, it's saying how much force is there going to be on the tugboat. And so really what it's asking is how much force is it going to take to get the barge moving, really? So the second part, so let's see, what is force on tugboat? And that's the same as asking how much force is required to get the barge up to speed. Because that's going to be the only force. So in other words, the only force on the tugboat is going to be the force that it has to deliver to get that barge up to speed. So we can sort of focus on the barge then. So barge here, 75,000 kilograms. And again, this is the force from the tug. So question is, how much force is going to be required to get it up to speed? So we have like M1, V1, plus force delta T. Once again, we don't have to integrate. M2, V2. Again, it's starting from 0, so this thing's going to be 0 here. And then plus so this is going to be the force from the tugboat. Times, what would we say, 25, 35 seconds, sorry. 35 seconds. And again, we're just looking at what it's taking for the barge to get up to speed. So our mass here is just the barge, because we're focusing on the barge here, seeing what it's going to take. So that's just be the 75,000. And then we know this final speed is 6.94 meters per second. And so the force that needs to come from the tugboat to get the barge moving, 14,871 newtons. Next, we're going to look at this problem, which is 15-15. And this one said the motor M pulls in the cable with a force of 10 T squared plus 300 newtons, where T is in seconds. If the 100-kilogram crate is originally at rest at T equals 0, time equals 0, determine the speed when T is 4 seconds. Neglect the mass of the cable and the pulleys. And now here's an important hint. It says first find the time needed to begin lifting the crate. In other words, on these problems where we're lifting stuff off the ground or pulling stuff, we have to be sure that we don't assume motion has begun before we actually overcome friction or overcome the weight of the object. So for example, here, the motor will have to run long enough according to that equation that F equals 10 T squared plus 300. It'll have to run long enough to generate enough force to begin it lifting off the ground. Because, if it doesn't overcome the force of the object, it won't begin it lifting off the ground. So we'll have to keep that in mind when we do this problem. And so let's see, what do we have? So this is coming down here. This is coming up here. We have a force up here. So we have something like this. We have a force. So again, we'll see what we have actually in this thing. So this thing here is down here, and then this thing is also underneath, kind of lifting this thing up as well, huh? So these are both lifting this up. And so if this is F, then this side also has to be a force F as well, huh? Remember from your pulleys, if this side is a certain force, then if you go around the pulley, this side has to be the same. Same thing up here. If this is F, this has to be F on this side. So we have something, like I said, sort of something like this. Yeah, and again, how we usually write these, we can sometimes write when we do this, when we do tension, we usually put them like this. But the point is that what we're going to have lifting the crate is going to be a total of 3 forces, F. So force lifting crate is going to be 3F. And so now let's take a look just at the crate itself. So we can sort of think about, like, we have 3F here. Now before it starts moving, NC is going to be, this is 100 kilograms. So NC is going to be 100 times 9.81. So it's 981 newtons. So that's the number of newtons before any force is applied. So this force has to be overcome before the box starts moving. So until that 3F is equal to this 981, the box won't start moving. So 3F has to be equal to 981 for the box to start moving. Now F, we're told in the problem that the force F is 10t squared plus 300. And so if we multiply this out, so again, I'm just following this through, 30t squared plus what's that, 900 equals 981. And so we have 30t squared is 81. If we divide this through and then take the square root, we get t is 1.643 seconds. So that's when the box starts moving. Because before that time, just the mass of the box hasn't even been overcome. So it's not going to start moving till that point there. So now we can start applying our M1 V1 equal M2 V2. And so let's first look at that integral. So just keep in mind what we're going to do is M1 V1 plus that impulse. So again, our impulse is going to be F delta T. And so we're starting to move at 1.643 seconds. And we want to see what happens after 4 seconds, like this. So again, what forces are we going to have? We're going to have a force that's going to be lifting it, which is going to be 3 times 10 squared plus 300. And then minus the force of, like, say, the mass. Now, this is up to you. You can either include that in the integral, but since you know that's going to be constant, maybe you don't even want to do that. So we may keep that separate. So let's do that. Again, you can do it either way. You could include an integral, but I'm just going to do it this way. I'm going to say, okay, the force, or I should say it's going to be negatives because it's going to be trying to resist the motion. So minus 981, this is the mass. This is the force in the crate from the mass. And this is going to be 4 seconds minus 1.643 seconds, like this. In other words, this is just going to be our, force from the crate, like say from the mass, and that this is going to be like delta T. Since that force is going to be constant, we don't have to include it in the integral. You can, but I just made it separate. It'd be a little bit easier to deal with it that way. So again, this is going to be resisting the lifting. And I won't go through all the details here. When you integrate this, you end up getting, let's see, this ends up being 4240 when you put the bounds in, minus 1523. That's this part right here. You can check it, but all I did was integrate this and put the bounds in, got this. Then that over here, this was minus 23, 12.2. And so this was 404.74. So now we just use our equation, M1 V1 plus the integral f dt equals M2 V2. We're starting at 0. And then we determine this over here is going to be 404.74. And the mass of the crate is 100. V2 is 4.047 meters per second. Next, we're going to look at 15-30. 15-30, a jet plane having a mass of 7 megagrams takes off from an aircraft carrier such that the engine thrust varies as shown by the graph. If the carrier is traveling forward with a speed of 40 kilometers per hour, determine the plane's airspeed after 5 seconds. Now, one thing to note in this problem is that the aircraft, the jet plane, is moving with the carrier until it takes off. So prior to takeoff, it's moving the same speed as the carrier. So keep that in mind. Again, this time we're given a graph that shows the force in kilonewtons over time. That represents, according to this, that represents the engine thrust of the plane. So this thing is moving, the velocity is 40 kilometers per hour. And that's 40,000 meters per hour divided by 3,600, which gives us around 11.11 meters per second. And the plane is 700 kilograms. So that's the plane going to be leaving. And we're given the force over here, time, force here. Now, so pretty much we're going to have to like find out what the total force is. So we have to sort of integrate it, but we can do it like sort of manually because we're given this little graph here. So if we have something like this, and we'll have to break this down now. Let's see, because it tells us. Actually, you know what? We're really only dealing with what's under the curve here, aren't we? So we're really just dealing with what's right here. So we can break this up into parts probably. So if we call this maybe section 1, this section 2, this section 3, like this. So really our force FDT is just going to be the area under the line. And so what we have over here, let's see, this is 2 seconds, 5 seconds, and then this is 5 here, 15 up here, like this. And so, yeah, we can just take the area under the curve. So like if you look under this triangle here, that's going to be 1/2 times the base times the height. So it's going to be 1/2 times 2. And then the height, now that's giving in kilonewtons. So this is kilonewtons. So I'm going to write it in newtons. So it's going to be 5,000 newtons. Then for this rectangle here, of course, rectangle is just the base times the height. 5 minus 2 times the height, which is 5,000. And then this triangle up here is going to be the base times the height. 1/2 the base times the height. So the base is going to be 5 minus 2, and the height is going to be 15,000 minus 5,000, huh? Like this. So that's just going to be 35,000. And let's see, what would that be like Newton? I guess I should be putting the dimension down. That's Newton second would be the units there. So now M1 V1 plus integral F dt M2 V2. Now this time it's leaving this aircraft carrier, right? So, and the aircraft carrier was moving at 40 kilometers an hour. So its initial velocity is going to be that 40 kilometers per hour. So this time, even though the plane wasn't moving, the barge was. So in effect, it was moving with the barge. So the initial velocity is going to be that 11.11 meters per second plus our 35,000 equals 7,000 kilogram times V2. And you put that in your calculator, 16.11 meters per second, like that. Again, remember this here, because the plane was moving with the barge before it took off.